Everyone. So I'd like to first start this week by correcting something that we got very confused about last time between the value function and the Q function. So basically the Q function we saw is that given a state and an action, right? What's the expected future reward? Okay, given state t and an action at that time, right? Okay, and the value function, okay, is the expected future reward only given state t, and this could be using any action. Now the thing is, this could also be shown as this for each action in the action space. Okay, this is the policy. That means the probability to take action A given state S into the Q value. Sorry. Okay. Which is basically the probability to take that action and the value of taking that action, right? Now you can show the relationship between these two. What we showed was V of S, but in this case it's only V of S star, and that means the optimal policy, and that means taking the best action. Okay, only then you can show that it's the max over all A for Q of S. Okay. So today what we're going to go over is DQN, which is a deep Q network. Now the reason why we have we use a neural network is because as you saw in last time's example, it was a very small observation space, right? It was a finite number of we said 500, right? But in most games the number of states could be infinite as well, right? And neural networks are basically can be used as a function approximator. So you're taking the observation, it could be an image or it could be something else. So we're going to use cartpole, and cartpole basically has each observation is a vector of 4 things. Okay, one is the have you all seen cartpole before? Okay, let me just show you what it is. Somewhere in the old one is not updated. Okay, so basically you have to control this cart and you have to keep the pillars straight, and you have only 2 actions, either move the cart left or right. Okay, and so the observation space is 4 things. One is the position of the the position of the cart. Okay, the velocity of the cart, the position, the angle of the pole, and the velocity of the pole. Okay, so it can be represented with just these 4 numbers, and I've taken a very simple example, so we're not going to go into CNN and stuff. We're going to create a simple feed forward network to do this. Okay. And a couple of things that you would normally also have to implement whenever you're doing this is so there's a problem called the temporal limitation, which, say for example you have an image in the game Pong. Okay, say one paddle is here and one paddle is here, and you have the ball moving somewhere here, right? So with just this one frame, you cannot tell which way the ball is moving. right? So there are two ways to do this. One is you have a stack of frames, right? So if you have a stack, so the next frame, say the ball moved here, so this is your second frame, third frame, and so on. And the other way is to use an LSTM. But most of the implementations I've seen is they use a stack because just to reduce the complexity. Okay, that's one. And the second thing is something called experience replay. Now, experience replay is used mainly because whenever you train a neural network, it tends to forget older experiences. So especially when you have different levels. So say for example in Mario, the second level may look completely different from the first level. So once you start training on the second level, it would tend to forget things in the first level. So what you do is you keep a memory and you keep writing to the memory. You could have a limit like a DQ, and every time you train it, you sample from that memory. Okay, and so it helps with two things. One is it'll help to retrain on older experiences, and second thing is it tends to remove the correlation between certain actions. So say for example there's a sequence that happens only when you take a particular action when you're training it, but you don't want that action to have an effect on the final outcome. So say for example, there was a case where you're an agent over here, okay, and you had two guns, one in your left hand and one in your right hand, okay, and a monster comes this side and you're supposed to shoot it, right? So if the first time you shoot it this side, and say he has a 70% chance, if he came from the right, he'll come again from the right, okay, but you don't want that previous. So it may form a pattern of it coming from the right 70% of the time, but you don't want that to affect it if it comes from the left, right? So that's why when you sample randomly, it tends to remove that correlation. Okay, now so let's start with the code. One thing is, so we're going to implement experience replay, but we're not going to implement stacking because in this case we already have the velocity, so we don't really need a stack over here. Okay, but normally when you have images, you probably need to implement a stack. Okay, and one more thing. So so this is the equation that we used last time for the normal Q-learning. So if you want to implement a neural network, your weight update, okay, is going to be, so I'm just going to show you this part. This part is the same. In this case, it's going to be your network. So S, A, and W, which is your weights, minus and this multiplied by the gradient over W So this thing here, this is your current predicted value. This is your target value. And this is your, this minus this is your TD error.
TD?
Okay. the temporal difference error.
Mm-hmm.
Okay, so let's go ahead. So I created a very simple code in TensorFlow, so it may not be the completely best, but yeah.
Or is it the same as last week or different?
So this is what we did last week, right? So the reward that you get at the current step plus the discounted reward from the maximum Q value over any action from the next step, right? And this is for the current, right? So you this was the difference. So here what we're doing is the same thing. This part is the same, only now we're using a network, so including the weights.
Oh, I see.
Right? And this is going to be again from the network, and then to optimize this, you multiply it by the gradient of your predicted value.
I cannot get the intuition. Can you explain why we multiply by the gradient?
So for a neural network, here you're going to try and optimize the parameters W, right? So this is your error, and say you're using mean squared error, right? So that would be half into this, your TD error whole squared. And normally whenever you want to optimize that, so you want to move it in that direction, you multiply it by the gradient of this. So in this case, the 2 will cancel, and it will be the gradient of your TD error. And in this case, your target value, although you're using this to predict the target value, the weights that you're changing is for your current predicted value. Right? So technically, if you use a Monte Carlo approach, you wouldn't even have this prediction. It would just be the actual rewards that you got over the whole sequence. Here you're just using this to predict it, and then this would be your gradient.
Okay. And I'm sorry, I don't get the. I think it's a very simple thing.
Yeah.
Why we so you show the delta W is this is the TD error different. So why we multiply gradient of W
So in a normal neural network, if you had some parameters, right? If you have a predicted value and a target value, and you say a simple mean square error,
yeah,
right?
So can you say we are basically doing this? So it looks like let's say this function so this one is some kind of, it looks like it's some kind of chain rule. Right. So we want get here. I can remember the correct. So, can you explain it in terms of the chain rule? I think it's
I know what you mean.
Yeah.
So this can be termed as y hat, and this is your current y. So for mean squared error, actually in this case it's directly here, right?
Yeah. Oh,
It's I mean
partial derivative over y, right?
right.
So
dy and then
Yeah.
dy by dw
yes,
and dE by d
that is the
error with respect to y. So if you take that,
it's a y
should be
and minus
2y,
one.
yeah, minus, sorry, this cancels,
Yeah.
minus y into dy is not that.
No, it's a y hat minus y.
No, but in it's the partial derivative with respect to y, so this will get removed, right? This is your predicted value.
Okay. Okay.
Into
No, it does not cancel.
so this is the partial derivative of this with respect to y minus partial derivative of this with respect to y. Sorry, this will become 1. Oh no, wait, I got it.
Yeah.
I got it. So this whole thing becomes 2 by 2 into y hat minus y,
Mm-hmm.
right?
Mm-hmm.
Into minus y. Okay, that's for d by dy.
No minus y, just minus 1.
Yeah, minus 1. And into dy by dw is going to be the gradient of
Yeah,
that,
that
right?
term, gradient
This term,
Yeah.
q hat s comma a comma w, and yeah, and then you can just replace it.
Yeah.
And one more thing is here you use, so this whole thing would be minus, so this whole thing becomes minus of this whole term. So I'm just going to write it as this,
Mm-hmm.
okay, into gradient of, but we are going to do gradient ascent because we want to maximize the reward instead of minimizing the error. So we'll change this term to plus.
Okay. Yeah, makes sense to me. Okay.
inputs. Then we're going to create a class DQ agent. We're just going to use some setters. Okay, one more import. Okay, a DQ is basically it's what do you say?
Double-ended queue.
Yeah, so basically if you have a queue of size 4, okay, whenever you input to it from here, it will remove the last one from here. Okay, so it will keep updating it with the newest one and removing the oldest one.
Kind of first in, first out there.
Yeah. Just 9555.
What is the state size mean?
The state size is going to be 4, which is the
So 4 vector.
yeah.
What will be the action side? It will be
Action size is 2. You can either go left or right. That's it. Okay, and okay. We're going to use a slightly modified version of the greedy epsilon. Here what we're going to do is we're going to start out with 1 and then keep multiplying it by the epsilon decay, so it'll keep reducing, so you stop exploring so much later on.
what is that max length? So that's like basically you can store.
Yeah, instead of 4 it'll be 2000. Okay, now we're going to create a model, TensorFlow model. This up.
Can you
Yeah.
check into the zoom out a little? So
Zoom out. Okay. Is that okay? One more.
So there should be some type of self that inputs.
No, this is just a placeholder.
Is there any space after inputs?
Oh yeah,
That
equal.
on the bar. there was some convention about the variable with underbar.
Underscore there's no real convention. It's just that if you don't want it to clash with any other variable, so if you define it in a different loop, then you don't want it to clash. Case the size is just going to be a scalar, so it's an empty bracket.
Can you explain what was the meaning of the underscore on the end, separate accent?
It's just a convention so that your variable doesn't clash with another variable called input. So if you're in your main loop, you're using the variable inputs, you don't want it to clash. That's it. There's no other reason.
What happens if we put empty on the size of the
so in this case, it's just a scalar. So you use this.
scalar?
A single value.
Yeah. Okay. Can you draw the network?
Sure. So your weights here are going to be 4 by 24. Here is going to be 24 by 24. And here 24 by 2. Okay?
Okay.
And at every step we're only passing one value. One record.
Okay. Is it there target underbar Q in this graph? Or
Sorry?
target underbar Q? Self dot target underbar Q.
In this? No.
Okay.
So this will just give you the
Action.
predicted Q value. So
Q value or action?
Q value for each action.
So input is
Input is the four from the state, right? And it will output a value, a Q value for action up. Sorry, action say left, and for right.
Okay, I see.
Units. What else do we need? Okay.
ReLU or ELU?
ELU is different. It's like ReLU, but it
It goes
Yeah.
below zero.
it goes and then it goes like that. And then Should I zoom out more?
Yeah, please.
You can copy this. I'm going to type it again for the next layer. Here your inputs is going to be the previous layer, units is going to be 24. In this case, it's going to be your action size. Okay, then we're going to go. This is just going to add it to your memory. Wait.
Oh, can you explain what is the self Q and self loss two line?
Self Q is now going to be your predicted value. Okay,
Predicted value.
and that is this. Okay, and self loss is going to be this minus that.
So the self that actions
Yeah,
is the
you will get a better understanding actually once we go through the main loop, and I'll explain it properly.
Okay.
Because basically the self dot action is what was actually happened. Okay, I'll actually show it to you because we're kind of running it twice over here.
Okay.
So what this is doing is you are checking again, like how we did last time for greedy epsilon. You take a random value. If it's less than the current epsilon size, take a random action. Otherwise, run the TensorFlow session, passing the state, and run it only for output. Right now, you're not training anything. Okay.
Do we need to reduce the epsilon value here or no?
Not over here, because we're doing it after every episode, not on every action that you take.
Pardon me?
We're doing it after every episode, so maybe 200 steps, right? After one iteration of the game. This act is for one action that you're taking.
Okay.
This is going to create a mini batch from the memory, and so for state action reward state and done. So here you're running the session to predict the next state's Q value. Okay, and then you're going to discount it. So reward plus np.I will just create an identity matrix, and then you so basically you're one hot encoding the action. equal to After loss, I missed that equal to.
What is the A max? And no,
It's just the max value from an array.
max values from what?
From an array.
From
Array.
At,
An array.
array. Okay.
Okay. Variables initializer and I had to do some changes to get this to work, so I basically just converted them into a 2D array with one row, right? Because here it was just a vector of 4 elements, and when you're passing it to a TensorFlow model, you basically need minimum of 2 dimensions, right? So all I did was I created so the first dimension is one row with the same four values here.
Okay.
Not sure this is the best way, but this is what I did. Okay, so now for by keeping a limit of 500 steps in each episode, so it doesn't continue forever. The same thing to the next state, and
So what's the effect for batch size?
the batch size is only so whenever you're training, you're picking up 32 samples from the memory. But actually I'm doing everything with just one at a time. when I'm actually training it, I'm just passing one sample at a time to the TensorFlow model. You could probably optimize it by passing the whole batch and do it.
Okay.
But I've tried to make it simple.
So the batch size here is not used.
No, it's used only to pick up 32 samples, right? And then I'm training each sample individually using the TensorFlow model. And we're gonna give it a negative penalty if it gets done. Okay. So basically, if it terminates prematurely, that means it falls down. We're giving it a -10 penalty.
So there is only -10 penalty for.
If it falls down.
So if we survive one time frame,
I think that is +1.
that is perfect.
We can check that. Let's just. Yeah. Okay. So what we can do at each step. So if and so outside this for loop, let's just update epsilon. So in this case,
Is there colon? What does the colon mean on the print expression?
This
Yeah.
this is to format it with two decimal places.
Okay.
In that next state, underscore reward, underscore like comma done, then that's what is that underscore? Like
It means
next
we
state
will
without
use the variable.
Sorry?
We will abandon the return
Yeah.
value.
Okay.
So normally this is the information variable, and you in any of these OpenAI gym, like this variable is only used for debugging purposes. You're
Okay.
not supposed to train or use it for anything.
Okay.
So yeah. What is that? Okay, agent on epsilon. Yeah, done. Let me just see if it runs.
So can you show me the environment name?
The environment name is Cartpole V1. I used action somewhere instead of. Here it should be actions underscore.
Can you show the line number?
How
There
do I
is
do
an
that?
option for showing the line number.
View. Dot line. Around 948. Should be S and underscore. Self dot action.
Can you show me the Paul, can you go to the last line? This is last line.
Yeah.
Hold on. Can you?
Done?
Can you go to replay function? Some language.
Okay, one second. Let me fix this and I'll get back to you. Loss. Self dot loss. Yeah, and line 51, this should be self dot loss.
Where did you make a change?
Line 51, it should be self dot loss. I missed out the self. And what do you mean this? No.
Can you show where you made change?
Yeah, add self dot loss.
Self-optimizer. Let's see what things are.
State session. Something is wrong.
So it's the tab. So do you see?
Right.
Can you show me the init?
The indent?
Reduce the
Yeah.
screen. One more. Yeah. Go up. Go up. Go up. No. Go up. Go up. So this is the where the function begins.
Yeah.
And go below. Slowly below.
Oh, okay.
So all the function belongs to the init. Yeah.
It's new one step.
Thank you for that. You can just select this and press Shift Tab.
Yeah.
Oh, that.
Can you zoom in on the print statement?
A lot of mistakes. There should be agent dot memory, not agent underscore memory. Okay. And agent replay, it also should be agent dot replay, not agent underscore. Okay.
How do you shift this one? Tab.
Paul, can you go where it says reward if not done, where we reduce -10?
Here.
Where is that? I can't see anything. Content else. Okay.
It should be action underscore.
Where?
On line 79.
Okay. Okay, I am working now. So this is just a random, right?
Yeah.
It's getting many episodes.
Yeah.
It will get 1,000 episodes.
Right.
Right? Then why there will be a 1,000 episode, right? And each episode is up to 500
Timestamps.
time steps.
Yeah.
And we have a 2,000 DQ. So out of this 500,000 time steps, we randomly sample 2,000.
No, so how it's working is you have a memory of size 2000.
Mm-hmm.
So your maximum amount is only 2000 because this is a pretty simple example, it's not that complicated. And it starts training. We're going to play a maximum of 1000 episodes. So say in the first episode, what happened over here was it happened to reach 48, which is quite high, right?
Mhm.
So in your memory now, as soon as it reaches 32, okay, it will start training now at each time step. So at the 33rd time step, okay, it will sample from the memory. In this case, it will take with 32 values, okay, and it will train it on that. Then it will increase this to 33 and so on, and then it will keep sampling from this till this reaches 2000. So now at every time step it's still going to sample 32 values and train it on those 32.
Okay.
So what does the delta W correspond to in the code? E raised to
This last one.
So-
State is equal to
So we got the output over here. So the output was the Q values for the current action, right? And technically how this worked is you played the game taking your actions and then you stored it in the memory, right? So in your memory you have your current state and you have your next state and you have the reward that you got, right? So now using the next state and the reward that you got, you can calculate these values. So in this case, this is the reward that you have, which is directly there, that you stored, okay? Then what we did was we took the next state and we tried to predict the maximum Q value, that is over here. So if you see in replay, you have a target Q, right? You're running the TensorFlow model using the next state, right? And then we did the np.amax to get the max value, right? And you discount it, right? So you got this value, okay? And then what you're doing is over here, when you're optimizing it, you have passed the current action that you took. This is a one hot vector of either 1, 0 or 0, 1, right? So you multiplied it with the output, right? Because you're predicting it again. When you run the session, it will predict it again. You multiply it because this is the actual action that you took. So suppose it puts some score of 0.7 for say this is left and this is right. So say 0.7 for left, right? So it will remove this value, right? And then it will do the target Q minus Q and square it.
So from where you are calling replay function?
A replay function is from the main loop. At every time step, if we have enough memory, which is minimum batch size, it will call replay.
So, can you go back to the?
Yeah.
I think that was what Shadek asked. But can you explain line 48 and 49?
Okay, so 49 is simple. 49 is this, right?
49 is
The loss, right?
48. What about 48?
Okay, so 48 is so first in your main loop, you call this model only up till output, right?
Mm-hmm.
And you got a Q value, right? So you got it. So you got an action. Okay.
So let's say action for left is Q value for left is 0.7.
Correct.
Q value for right is 0.3.
So left was 0.7
Mm-hmm.
and right was 0.3. Okay, just say this was it.
Yeah.
So what you did was you converted it into a one hot encoding, and you took the max value. So you took 0.7, which is left,
Mm-hmm.
and then one hot encoded it. So you basically got 1, 0.
Where you do it?
Yeah. Oh.
So I would.
In replay, one second. Yeah. the np.I will create an identity matrix, and then you take action. So in this case, it will be 0.
Yeah, so I was thinking the line 48.
Correct.
Then this definition of function replay does not comes to
No.
line 48.
It does, right? When it calls the session.run.
Where
So this is where it's calling it, right?
close session. Okay.
So to understand line 48, you need to understand what is being passed to this model, right? You need to know what actions is over here.
Actions is okay. Now I understand. So actions is input and
Correct.
output is the
What you predicted.
network.
Yeah.
Yeah. Okay, I see. So the actions comes from the function replay.
Right.
Okay. So
Scroll down. Yeah, the replay function.
Did you get it?
okay, so now so can you I'm really sorry.
No,
Can
no
you
problem. No problem.
again explain line 69, line 74?
74. So 74 is basically let me do it in code. It will be easier for you to understand.
Hello, do you guys have a reservation?
Yeah, right now.
Okay, I think our reservation is on the 2 p.m.
Paul, can you share this thing that
Yeah.
my thing is